Hello, everyone, and welcome to the Underwater Robotics live stream from the Coral Sea as part of Science Week and the Sydney Science Trail. It's great to have you all joining us today, and I'm very excited to be able to share some of the incredible work that's currently being streamed out of the Coral Sea on the RV Falkor done by the Schmidt Ocean Institute. My name's Peter Tattersall. I'm the Head of Learning at the Australian National Maritime Museum, and we're incredibly excited to have you all here today. Now, before we go any further, I just want to give a quick acknowledgement of country to the traditional owners of the lands on which we all are sitting today, a variety of places across the globe, in fact. Look, the way we're going to do this today is I'm going to throw across to Carly Wiener, who's sitting in Hawaii. She is the Director of Communications and Engagement Strategy at the Schmidt Ocean Institute, and she will then pass us along to onboard the RV Falkor. I will mention that we do have a chat function at the bottom of your screen, so if you have any questions, please type them in there, and Carly will be very happy to send those questions over to the scientists aboard the vessel. Without further ado, I think I will pass over to Carly and say thanks.
Thank you so much, Peter. Schmidt Ocean Institute is so pleased to be here today, and we are even more ecstatic to be diving live right now in the Great Barrier Reef as we are doing this connection. So we are very appreciative to our ROV pilots, to our scientists, and to our crew aboard research vessel Falkor who are making some time today to talk with us. So I'd like to start by introducing them, and then we can go on from there with some questions about not only ROV Sebastian and learn a little bit about what Sebastian does, but also why it's important to use an ROV and the type of science that our scientists are doing with it. So without further ado, I'd like to throw it over first to our science control room where our ROV pilots are sitting. There they are. We can see them. Hello. With us today, we have two incredibly talented pilots, Jason Rodriguez, otherwise known as J-Rod. He is Falkor's ROV pilot and one of the ROV supervisors from Texas, as well as Cody Paris is also an ROV pilot technician from Texas as well. And with us in our library today, we have three scientists. If we could have our scientist wave and say hello. We have Antonella Willoughby, who is a PhD student in the Contextual Robotics Institute at UC San Diego. Alex Post, a marine scientist, geoscientist, at Geoscience Australia, and Dr. Steph McLennan, who is a geoscientist as well, who does a lot of work in Antarctica. So we should have a very interesting conversation today. First, we will go over to Cody and J-Rod. And why don't you guys start by telling us a little bit about what you're doing right now?
Hello, everybody. My name is Cody. I am right now piloting Sebastian. I'm flying Sebastian down to around 1,500 meters, and I'm trying to keep up with the ship as we go.
And I'm J-Rod, like Charlie said, and I am making sure that the vessel is moving along the track that we are traveling, giving it new waypoints and staying in communication with them, and also making sure that our winch is paying out at the proper speed to keep up with Cody as he goes down.
Fantastic. And you guys have a very important job. First of all, it's so amazing to be able to take a peek into the science control room during a live dive and see what's going on and what's behind the scenes. There's a lot of buttons and lots of things over there that look like looks like video game control buttons. Tell us a little bit about what we're seeing and how you use them to control our underwater robot, Sebastian.
All right, we'll start with Cody with the main controls for the ROV.
All right, guys. So right now, this right here is our main joystick. I am flying Sebastian forward, and also right here on my left hand, it's a little paddle. That's my vertical thrust. Right now, I'm thrusting down to keep up with the winch at a set speed that we have it set to. So I want to keep that winch going 30 meters a minute, and I'm heading down at 30 meters a minute just to keep it equal. All these buttons right here are all of our different valve packs. They do different things. Moving up the sit cam right now. They bring in the porch, bring out the porch, open up bio boxes. They run we call them sock and bottom rails now. There are rails that we put core tubes on and other coral quivers, and we changed them because we're going to be working with rocks, and it's great to push them out and get stable when we're going up on rocks and different cliff faces. Then right here is my main touch screen. I use that to control all my lights, cameras, sensors, turn on my sonars, and let's see what else. Over here, I'm going to come over here, Dean. These right here where my left thumb is, right there is all the camera controls. I can get my focus, mess with the iris of the camera. Then over here are all my thrusters. I can sit there and bring up the percentage of thrust, and also bring the percentage of the thrust down that I want to use. That's about it for these controls. J-Rod's going to take it over and show you what the T4 can do on all the other controllers.
All right. Well, first I have the backup camera control. Cody has one over there as well. But this is typically the one that the chief scientists use when we're flying around and they want to zoom in and have a look in real tight on something. Cody can use the camera over here. They would have this. They have autofocus. They have iris controls. Sorry about that. They have all the iris controls, autofocus and zoom with this one. Normally I wouldn't have this here. Like I said, the chief scientist would have it, but we use it when we're doing the mid-water aspect of the dives. This controller right here is for the arm that you see in the camera right now. If you look at it, it has all the functions that that arm does. So when I go live with it, I hit a little button right here and it unfreezes it. And as I move it out, it does everything that I do in real time. And currently I have a suction sampler in there. This is what we use to slope up sediment, jellyfish, all kinds of things that the scientists would like us to sample for them. I can open the jaws and unlock them real quick. All right. Jaws can open up and it has full 360 rotation on the wrist. The jaws can close down with force of about 900 foot-pounds, which is enough to break some bones, but it's also precise enough that we could actually pick up something as small as an egg or as fragile as an egg. We'll put this guy back away real quick.
That's incredible to see all the different instruments and utensils that you use to do some of your sampling. And a lot of those controls that Cody and J-Rod have just been showing us also help to control the lights and the cameras. So J-Rod, why don't you tell us a little bit about why it's so important to have so many controls for lights and cameras? What do we do with Sebastian that makes that so important?
Well, with the camera that we're using, the 4K camera, there's no light at any of the depths that we're operating at. And so we need a lot of light in certain instances to be able to see far. And then we also need stuff to be able to look close up. And if you use the same lighting to see far as you were trying to look close up, everything would always be washed out. So we have to have the ability to turn our bright lights off and just keep our close little lights on and make an adjustment on all of them just to get the lighting perfect for whatever specimens we're looking at or scenario that we're in.
Thank you. That's amazing. And that top-down view we get of Sebastian's bio boxes and some of the core samplers, can you tell our viewers a little bit about what they're looking at there?
Okay, do they have that feed right now?
Yes, that's what we can see right now.
Okay, I'm gonna bring the porch out. So this is a porch coming out. So this porch is able to slide all the way out from whenever we're doing samples. We keep it in for doing all the filming because as you can see in the 4K camera right now, it would get in the way. Looking down, you see that we have 4 bio boxes. We have the 2 in the back that Cody is opening and closing the lids. That one's actually opened up, and it's one big bio box to take really big samples. The 2 in front of that, the one on the left is divvied up into a quad, so we have it as A, B, C, D, so that the scientists, when we take the samples, we're all on the same page as to what box we put it in. And when we come up, they know exactly where they got, what depth they got it from. And then we also have a third bio box number 2. This one's a little bit bigger, and it's full of tools. We have a scoop in there right now that allows us to get different kinds of sediments, or sometimes pop off something like a cup coral. We also have a hole saw that we put on the T-handle to be able to drill into some of these rocks that the scientists have been wanting to get that we can't actually break with a MNIPS alone. And we have a new addition, and it's like a pry bar that we can actually go in and break rocks. Off to the left, you'll see 8 little handles. Those are actually for taking core samples of the mud. So we can push that into the mud, and it has a one-way valve on the top of it. And as it goes down, it lets the water come out the top. And then when we go to pull up, it makes a vacuum, and we can pull out the sample. If the sediment's just right, it will stay in. If it's a little too loose, it still might fall out, and we have to go really fast. You'll see those little zip ties underneath the those O-rings. That's actually to allow the pressure to equalize on the way down. If we didn't have that, some air would stay trapped in it, and they would actually implode on the way down. And so as we pull the core out, that zip tie will pop off and allow us to take the sample properly.
That's amazing. Thank you so much. It's so nice to see all basically your toolkit of what you can use to collect the samples. And you know, one of the amazing things about the ROV, it allows you to have such precise sampling, so you only take what you need. What has been some of your experience in doing these samples? What's been the most interesting sample you've taken, or most surprising so far on this expedition?
There's been a lot on this cruise for just unique things that I haven't seen before, and that even the scientists haven't seen in Australia. And so there's been a lot of firsts. So it gets very exciting all the time with the samples. If I had to pick one that was my favorite, I would have to say probably some of the midwater stuff that we've been doing, because we've actually had to kind of fine tune our suction sampler to be able to slurp up some jellies and not destroy them. Normally we have the suction sampler to where we're able to vacuum very hard and get like sediments and rock, and that would tear up the jelly as it went into the suction sampler. And the way that we have it fine-tuned, we're able to actually preserve them whole.
My thing was probably we sampled an acorn worm yesterday. A pretty cool looking worm, subsea. It was on the seafloor as we were flying by doing a transect. And the acorn worm was pretty neat looking. It was the first one sampled here, or second one sampled in Australia. So pretty neat, pretty cool little snippet there. Second one ever sampled here in Australia.
That's amazing. So I have a lot of classrooms joining us today. I definitely want to give out a shout out to Kelly Plains Public School, Pleasant Heights Public School, a lot of other students, Mayfield East Public School. So those of you watching, please feel free to type in your questions. I'm sure some of our viewers are wondering how you got to do what you do. So how do you become an ROV pilot aboard a research vessel in the middle of the ocean?
So I started in the industry right out of school. It's a good thing to have a trade, electrical, hydraulic. J-Rod, I believe he was in the military, so he picked up a trade in the military. So, and yeah, once you get a trade and you just start flowing with it, start connecting, and before you know it, you get on a scientific research vessel and flying an ROV in Australia.
Yeah, for me, like Cody said, I was in the Navy for 8 years working in aviation electronics, and I got out, and perfect timing for the oil and gas industry was booming at the time. And back in the day, for there, whenever you started off, you didn't actually get to fly the ROVs. You had to do everything on the back deck, control the winch, clean everything, while the pilots were inside doing all the fun work. And after a good year, that's when I started being able to go inside and learn how to do the operations inside, which you only get to do a little bit at a time. When you're operating this co-pilot position, you're watching the pilot's back as he's flying, and you have to understand all the different screens that nobody looks at in this control room. Most everybody's just looking at the 4K. And it takes a while to get your eyes familiarized with all that, because once you become a pilot, it's really easy to get tunnel vision, and you need to have that background to be able to see the full picture and not focus in on the pretty stuff.
Which is very hard to do sometimes because everything's pretty down here. Especially when we start getting into the coral reef, it starts looking really nice. And being a pilot sitting there flying. Luckily, you have a good co-pilot by your side that can sit there and tell you what to do, what not to do, and it always helps. Kind of like flying a plane in a way.
So another question we get a lot of times, Cody, that's great that you bring that up, is why we refer to it as flying and pilots. Do you want to take that one?
Pretty much, the ROV has thrusters on it. So in a way, it is kind of like flying, I guess you could say, a helicopter.
It flies in the same axis as a helicopter.
So right now I'm pushing forward and it's going forward. I pull back, it's going to come back by lateral port. It's going to lateral port, and likewise going starboard and rotating port and starboard, as well as using my verticals. If I come up on the, pull up on my pad, I'm flying up. If I go down, it comes down. So push forward, pull back, kind of like a helicopter. If you really think about it, we're pushing through water and it's just flying through water, kind of like it would fly through air if you were a drone. You know, think of a drone that's you send up to the air and you're flying with a little controller. You're flying the drone.
Like FPV.
Yeah. But this right here is you're sitting with a full console and you're underwater. You're not inside the sub, obviously, because it's remotely operated, but you're on the top and you're flying that sub underwater.
J-Rod, a lot of people wonder, so ROV stands for remotely operated vehicle, but it's hard to understand when you're flying the robot how it relates to Falkor and the ship. So can you talk a little bit about the umbilical and how the ROV is attached to Falkor?
Yes, I can. Like Harley said, the vehicle is not battery operated. It is not remote control in the sense of an RC car or a drone. It's with a tether. It's connected by a wire. Inside, it's an armored umbilical that can handle 20,000 pounds of braking force. But it also inside has 5 conductors for electricity and 6 fibers. So although it's very strong, it also has some very delicate components on the inside. We have to send down 4,500 volts AC to the motor because to be able to supply the hydraulic power that we're needed, we need an electric motor that spins fast. But to be able to do that at a low voltage, it would actually take a lot of amperage, which would melt the wire. So we actually have to send higher voltage but lower amperage. And then we end up just using one fiber mainly for all of the controls for the ROV and most all sensors. The 4K camera and the stick camera require one fiber just for them because that's how much data is required for a 4K camera.
Excellent. Thank you so much. Another question that's come in is what your day-to-day job involves. So it might be nice if you both could talk a little bit about what you do when you're not flying the ROV.
A lot of coffee. No, we're not flying. So our normal shift is we'll wake up in the morning, eat our breakfast, drink some coffee, and then we hit the back deck and we do a pre-dive check. So we check Sebastian through and through. We have a full list. I think Gerard has it right in here. We have a full list of things that we know what to check. Make sure our oils are good. Make sure all the connectors and cables are good, because we're sending electricity subsea. And if one of the connectors aren't tight, we're going to have issues. We're going to have a ground fault, which is water entering electrical cable and causing it to ground out. Now, when that happens, we'll have to abort the mission and come back to deck, which we really don't want to do, because then the scientists get upset with us in a way. But we hurry up and try to make it, make it work. Then we fly for about 10 hours, 8 hours. All depends on what the said mission is. We'll retrieve Sebastian back to deck, recover, put it back on the valve port, and then we do a post-dive check. Within that post-dive check, we check everything that we checked for the pre-dive, just in reverse. We put camera covers on, we clean Sebastian, we do a freshwater rinse. We make sure there's no salt water on Sebastian, because it'll start corroding stuff away. And then we'll go in and check the cables, make sure nothing got loose while Sebastian was down. We'll check the oil, make sure there's no water in the oil. Now, previously we made sure oil was in there. Then post-dive, we make sure water's not in the oil, because then that means we'll have a leak somewhere. Something's filling a void.
Earlier, we actually had kind of a issue this morning, to where yesterday's post-dive check, we did it properly and everything checked fine. And this morning, doing the pre-dive checks, which normally you would think if you put Sebastian to sleep and everything was fine, that in the morning Sebastian should be fine as well. But one of the techs found that we had an issue in one of our valve packs, and had they not caught that, then we would have gone down, and shortly into the dive, Sebastian actually would have not been able to fly at all. We would have had to pull Sebastian up manually without being able to get any controls. So little things like that really save us.
We're lucky to have you guys to do all those checks. That's really, really important. We have a question from Catherine Little, one of our viewers today, who asks, how big is Sebastian?
Sebastian is about the size of a Volkswagen Beetle. Maybe weighs about the same, 3,200, 3,000 kilograms. 3 kilograms, 3.2.
I was always surprised how much larger Sebastian looks in person than when you see it on the videos. It's always kind of nice to see. Another question from Bruce Zoom: has a shark or big fish ever bumped or attacked the ROV before?
Actually, in Perth Canyon, me and J-Rod were doing a post dive. So normally when you fly in the ROV, you have a group of 4 guys. But doing a post dive, we had to do a different kind of shift change to where it was extended 12. So it was just me and J-Rod, and it was dark. J-Rod went in to go check some oil, and there was actually, what kind of fish was that? It was a lizard fish, tons of teeth. This thing looked freaky. It was very scary looking, and it was staring right at J-Rod as he was reaching in, made him jump back, and it was in on a cable, bit down on a little cable. Luckily, it didn't puncture the cable. It actually punctured the Kevlar that we have wrapped around it to protect the cable, and it rode all the way up to the top with us. So yeah, it's happened before. And then every once in a while, you get some big fish that will bounce the back of the sub, or they'll come around the side and see what you're doing. But no shark yet. No shark. We're in for the day.
Well, lesson learned. Look out for those lizard fish. Thornton Public School, hello, thanks for watching today. They are asking, how do you check to make sure that Sebastian isn't going to get crushed as it gets deeper and deeper?
how do we make sure it doesn't get crushed?
Yes.
That's a very good question. Any of the housings that we have that aren't a 1 atmosphere housing, they're actually compensated with oil, and it has a spring pushing on a bladder that puts about 7 psi, almost an atmosphere, over ambient pressure, so that as we go down, the forces pushing into that housing, it's also helping that spring push harder. So it's always going to be that 1 atmosphere over ambient, no matter how deep we go. Now, for the 1 atmosphere housings, those things have to be engineered and very precise, because if they're rated for 4,500 meters and we take it just past that, there is no spring pushing out on that, and it will cavitate and implode.
So in other words, don't try this at home. You can't just put anything down in the deeper water.
There are a lot of challenges.
Excellent. Well, we have another question from Pleasant Heights Public School. They're wondering how long Sebastian can stay underwater.
Well, Sebastian can stay in the water as long as we have fuel on the boat. Technically, it's always good to bring Sebastian up and make sure nothing's going wrong, nothing's gotten into the thrusters. But because the vessel has generators on board that are supplying the electricity for us, in a perfect scenario, Sebastian could stay down as long as we had the crewing for the whole cruise. But I don't think the scientists would like not getting their samples up every day.
And we're going to ask one final question and let you guys get back to the dive. I know how busy you are and you're in the control room there. Kelly Plains Public School has come back with another question and asked, how can you go so deep? We've also gotten a couple other questions about how deep Sebastian can go. So maybe you could speak a little bit about the depth.
So Sebastian is rated for 4,500 meters. When we say rated, that means that, like J-Rod was explaining with the boxes that we have on Sebastian, with the oil-filled boxes, with the control cans, they're rated for that pressure that's at 4,500 meters. If you start going over that 4,500 meter threshold, we'll start losing some of the cameras, or we could start losing some of the lights because they're not going to be working properly because all that pressure is pushing down on them. Now, on our umbilical side, we actually have a little bit more than 4,500 meters on the actual umbilical. And that's just for safety precaution and for us to actually create this thing called a delta, which is a catenary system inside of Sebastian, on Sebastian. And as J-Rod's doing right now, he's keeping my delta at 65 while I'm coming down. If it gets too big, we have too much of a spring. Think of it as a big spring on Sebastian, help kind of with the heave of the ship and keep that umbilical up and out of our way. Because the umbilical is heavy. It's an armored umbilical. It's not light. It's not floaty. It's armored. So we put floats on that umbilical. But that's about how deep Sebastian can go. We don't really
Fantastic. Want to go. And one last thing before we leave you both, Wyatt and Abby asked, do you like to play video games when you're not working? It looks like what you do is like playing video games.
That's our training. When me and J-Rod get off, we go on to the PlayStation.
That's a great message. Good message for all of our viewers. Play those video games if you want to be an ROV pilot. Well, thank you so much, J-Rod and Cody. I really appreciate you taking some time to talk to us while you're flying Sebastian. This is really incredible. I'd now like to jump over to the library so we can talk to some of our scientists on board. Thanks. Bye-bye. Excellent. And with us now, we have Antonella, as well as Alex and Steph, who are all part of the science team on board Falkor. Welcome. Thanks for joining us.
Thanks for having us.
Excellent. Well, I have some fantastic questions for all of you. I'm so curious to know how the science is going. Antonella, let's start with you because you're kind of doing this interesting straddling between some of the engineering and the science, and you have your own ROV. Can you tell us a little bit about that?
Yeah, absolutely. So I'm actually working on my PhD in marine robotics, but applying marine robotics to marine biology. So if you see here, the ROVs on the camera, it's a teeny tiny ROV. There are a lot of differences from Sebastian. It doesn't really work the same way. But it's intended to be a research platform for me where I can collect data and basically program the robot to navigate using only its cameras. So it has actually 2 downward-facing cameras and 2 forward-facing cameras and some other sensors on board, lights and thrusters. And we teleoperate it, but we're using it as a data collection platform so that we can basically program sort of the robots of the future that can do more sophisticated things without actually having a human control them.
Now that's quite a size differential between Sebastian and the little robot you have there. How deep can the robot go and how long can that one stay underwater for?
Yeah, so this one is actually, well, right now we're limited by the buoyancy foam we have. So the buoyancy foam will crush at 100 meters. And so that's our limitation at the moment. And it has battery power on board. So unlike Sebastian, that we're talking about, has the power coming over the tether, we have 2 onboard batteries on this guy. And that is sort of our limiting factor because the thrusters take quite a bit of power. When we're working in environments with high currents or high swell, it's burning through quite a bit of battery power. So anywhere from an hour to 2 hours in bad conditions is kind of our runtime. So it's a lot less sophisticated than Sebastian, but we can get some cool data with it still.
And have you been able to put it in the water and test it while you've been on board so far?
So tomorrow, actually, I've been testing it up on one of the decks in a tiny little tank that the crew built just to get it ballasted. So one of the issues, especially with a vehicle this size, you want it to be almost neutrally buoyant, just very slightly positively buoyant. And that's for, we want it to be able to come up again if the tether gets cut, and that's just for ease of flying. So we want as close to neutral as possible. It's using less power to keep itself level in the water column. And so, but obviously that changes. So we were in fresh water, it was all ballasted. Now we're in salt water, and even in different parts of the ocean, the buoyancy changes very slightly with changes in salinity. And so, yeah, so we put some water straight from the ocean into a tank, got it all ballasted, got it all tested. And then hopefully tomorrow we'll go off while Sebastian's in the water. We'll deploy this a little farther away from the ship and get some data. So we're really excited about that.
Fantastic. Thank you so much, Antonella. And Steph and Alex, I want to ask you a couple questions. How does the ROV work for your science? I mean, how important are the samples that the ROV is collecting for you to be able to do your work?
Yeah, so the ROV is just amazing in the capabilities that it brings. So normally, if we're collecting rocks from the seafloor or sediment cores or biological samples, we're fairly much collecting these things blind. We don't have a picture of the seafloor where we're collecting them. And we might be having to drag like a great big chain bag across the seafloor to try and get any of those rocks, get any of that biology. And so you actually don't really know exactly where your samples are from. They're not coming up in very good condition. A lot of them have been, tossed around inside a net or a chain bag. And so it makes it really hard to identify the organisms that you've collected. Whereas the ROV can just take a little tiny sample in its claws, pluck it exactly from the seafloor, the exact sample you want, knowing exactly where that's come from. And so then you can actually combine that with all your other data sets that you're collecting at the same time, all the sensor data on Sebastian that tells you the temperature, the salinity, the oxygen content of the water, all that information that you have about where that specimen was from. Was it sitting on a rock? Was it sitting in the sediment? And so you can really build a much better understanding of the ecosystems and the environments that you're studying. So it's just really mind-blowing.
And Steph, how do you process the samples, or what do you do with the samples once they come up from the seafloor? So Sebastian comes on board, what happens next?
So when Sebastian's doing a deep dive, all the scientists, we're in the control room, we're watching what's coming through the cameras during the day, directing the pilots to collect the samples and put them in those bio boxes and those sediment cores that you saw earlier. And then when Sebastian finally comes to the surface, we then head out on deck and then bring those samples back into one of the labs on board. And we spend a few hours going through those samples, preparing them, preserving them. It's like Christmas, really. Like every single day is a little bit like Christmas, where we've seen them collected from deep in the ocean and now we actually get to hold them in our hands. There's a whole range of things that we do with the samples. Immediately, particularly with the biological samples, they need to be kind of preserved. As soon as they're brought out from the ocean, they start to degrade and break down. And so the biologists set about preserving them so that they can be analyzed later on by different scientists, whether that's for DNA analysis or looking at the particular species that we might have found that day. For the geological samples, the rocks and those sediment cores that we collect, we'll photograph them in a lot of detail. We'll make sure what the scale is of it, start taking maybe some smaller samples to send to different collaborators. We'll bag them up and make sure that they're nice and stable and protected so that when we get back into port, they can go to different laboratories, universities, different institutions, and go through a whole range of analyses with those scientists as well.
And Steph, has there been any samples that have come up for you yet on this expedition that have just, so really surprised you or wowed you?
Yeah, one of the samples that I'm really enjoying seeing coming up is actually those push cores. These clear cylinders go into the seafloor, and it's sticky mud. If you were standing on it, you would start to sink. And then they pull up maybe 20 to 30 centimeters of mud. And when we bring that to the surface, when you first look at it, it kind of just looks like brown clay. But when you get in close, you can see actually where worms have started burrowing deep into that ocean, into the seafloor, making their homes, leaving behind traces of life. We can see evidence of old big debris flows where lots of debris raining out of the oceans and coming down these canyons has been deposited hundreds, thousands of years ago. They're a really amazing record of the processes going on.
Wow. Antonella, Alex, how about you? Any samples that you've been really impressed with or that have caught your curiosity?
So I actually brought one to show. If I'm not sure if you can see this one here, but
I love this show and tell from the sea.
Yeah. So we saw these guys on the floor, these little kind of mesh mounds, and what they are is actually the structure built by a single-celled organism. And so you see them quite a bit in the deep sea apparently, but they're just so amazingly intricate. Hopefully you can see sort of the honeycomb texture on this. And this is made by a single-celled organism. I just feel in awe of this thing. So it's actually called a benthic foraminifera. And yeah, they just gather up the grains from the surrounding sediment to build this structure. And there's quite a variety of different ways that they can do this. But the ones we've been seeing are these mound-like structures. And I just think they're beautiful and an incredible sort of way that nature just adapts its surroundings to something really beautiful and amazing.
Well, I don't have anything to show and tell, but I think some of the jellyfish that they've been slurping up with a suction sampler are particularly cool. I think they've maybe discovered some new ones, or I don't know what they're going to do with them, but I think it's going to be, or I'm sure they'll discover something really exciting.
Excellent. And I want to take a moment here to remind our viewers to please make sure to type in your questions for our scientists. If you have any today, we'll be able to answer them for the remainder of the time we have with Falkor. And Danella, I wanted to ask you another question. This is your second time out on Falkor, first as a student opportunities participant. So you got to participate as a student, and while you're still a student, you're developing your own research this time around. What's it like, and how is it different the second time?
So the first time I was on a transit where it was a smaller crew and there were no ROV ops. So it was kind of, we were doing mostly multi-beam mapping. I got to work with some of the marine techs to learn how to process that. It was sort of interesting for me because as someone that I work a lot with sensors and perception, but from the vision side, I don't do a lot with sonar. So it's sort of interesting to see how those two can work together potentially in the future for my work. I know we already use that stuff for the ROV navigation. So that was really cool to sort of see that different side that I hadn't seen before. Now, I've been really excited to see all the ROV ops, see the ROV up close. I've worked on other big ROV systems as well, in addition to this small one. So it's, you see some similarities, which is kind of cool. Like, I've worked on that camera system, but then there are other differences. Each vehicle is sort of, especially for science, a lot of these vehicles are just custom, like one-off builds that Sebastian is unlike any other vehicle in the world. And so that's really cool where, so in some ways I anthropomorphize robots, but I think they kind of each have their own personality of both of the things you need to keep an eye on, like what's going to break, what might be a little finicky, and just the things that you can do with them. So that's been really fantastic just to see Sebastian up close, have a go on the manipulators and all that. So
I'm so glad you're getting that opportunity to get to drive Sebastian a little bit. Alex, your fascination with the seafloor and seafloor bathymetry, what is so intriguing about the seafloor to you, and what do you love most about studying it?
So I just really love seeing what's down there. You always, I don't know, before I started looking at the seafloor in detail, I thought it was just all mud, that it was just all kind of what you see when you go to the beach. That was all there was. And then you start realizing that actually all the features that you take for granted on land of, great big mountains and canyons and pinnacles, it's even more amazing under the sea. These features are on such a massive scale. And so some of the canyons that we've been mapping on this voyage, they're as deep as Mount Kosciuszko is. So, and they're actually relatively small on the scale of a lot of canyons around the world. So just the scale of those features. And I also love the fact that you might have an idea of, we plan our transects thinking, this will be a nice rocky face where we're going to see lots of, deep water corals and things. And then you get down there and it's just something completely different than what you expected. And so sometimes you think that you're looking at the seafloor to understand it and, to answer your questions. But often you come back with more questions than what you started with. And so science is just fantastic in that discovery. You always have more things to learn. You never get bored. And yeah, it's just amazing the things that you can see and discover. And can I take the opportunity just to, can I give a quick shout out to Chapman Primary, Mr. Edmonds' class in particular, and my daughter Dea. Hello.
Yay, well, I'm so glad that they're able to watch today and join us. We actually have a question from St. Joseph's East Maitland School, and they have asked how the use of marine robotics has changed the study of the ocean compared to samples collected prior to robots.
Yeah, I think it's really about knowing exactly where that sample came from. Before, we might collect a sample and not know exactly what depth it came from. And so on this voyage, some of the corals that we've been imaging with Sebastian, it's actually increased the known depth range by, tens of meters. And so knowing exactly how deep some of these corals can grow, just provides us with much more understanding, especially, their vulnerability to effects of ocean warming and changes in the composition of the ocean, so that we can better know how to protect these corals into the future.
And Steph, a question for you. Your background and your work primarily takes place in Antarctica. How does this expedition and the work here differ from the work you typically do?
This expedition with my usual fieldwork, they are, excuse the pun, but poles apart. So literally 6 months ago, I was in Antarctica. I spent a few months down there doing fieldwork in East Antarctica. And, that kind of fieldwork where we're heading out, it's land-based, actually. I'm usually an onshore dry geologist. So this is definitely a voyage of new things for me. We're doing helicopter-supported fieldwork and taking geological samples there. The first thing I've noticed about being on this voyage is it doesn't take me 20 minutes to get dressed in the morning. I can throw on shorts, a t-shirt, and I'm good to go, instead of 3 or 4 layers of clothing and having a survival pack with me. This is, a really amazing voyage for a whole range of reasons. The ship that we're on, the crew that are staffing it and helping us make the most of Sebastian and the different sensors that the ship has, our ability to use this really state-of-the-art technology to see Sebastian take samples with surgical precision, being able to image the seafloor, see it live, bring up those samples and process them. The range of scientists on board, from biologists to, coral experts to jellyfish expert to geologist. I'm learning so much, and it's really important work as well. And it's a real privilege to be a part of that, for us to be seeing the origins of the Great Barrier Reef, the geology that underlies the Great Barrier Reef, and a really important part of Australia's history, to give people more information and more evidence to help protect it and manage it properly into the future. It's awe-inspiring. Yeah.
So amazing that you get to have that opportunity. We have a question here that's come in from our viewers. How many samples are you taking each day? Anyone
So
want to answer that?
Yeah, it kind of depends exactly where we are. What we're limited by is how much we can fit in those bio boxes and those push cores. So we can take up to 8 push cores. So that's that tube sliding into the seafloor and pinching some of that sediment up. And then we have a whole, few boxes that we can put rock samples into, corals, and then also jars that take anything that we suck up, often jellyfish or really fragile corals or sponges. I'm trying to think, yesterday was a pretty big day. We had, I think, 4 push cores, maybe sort of 4 different jellyfish, and then I think maybe 4 corals, something like that, and a sponge. Oh, and the acorn worm. It's a real mixed bag of stuff to process at the end of the day. It's lots of fun.
Great. And another question, this might be for Antonella, that's come in, is how fast can some of these underwater robotics systems go?
Oh, that's a good question. I'm going to say it depends, because it really depends on the sort of what's going on in the environment. In really high currents, if you're going against the current, you're going to be slowed down. I don't really have like a number in terms of knots that they can really go, unfortunately. But I'm going to say like decently fast, like not fast in the way you'd think of as a car, but I like, for example, I have raced this robot in the swimming pool and it can definitely beat me. I'm not particularly fast, so that doesn't tell you that much, but they're I think, yeah, they're pretty zippy. But yeah, it's kind of a hard question, and every system will be very different depending on the thrusters. So the thrusters on board can produce an amount of thrust, and that impacts how much or how fast your vehicle can go. But there are also other factors. ROVs tend to be very non-hydrodynamic, whereas like AUVs, which is autonomous underwater vehicle, those oftentimes will be shaped like a big torpedo. So they optimize the ability to be really hydrodynamic and go for a long period of time over their ability to do really intricate manipulations. What we get with the ROVs with, they have multiple thrusters on board. They use more power, but that also allows you to keep your position steady in the water. Alex mentioned working off these rock walls. You really couldn't do that with an AUV unless it was very sophisticated, but not many, I don't know of any system right now that could really work in the same environments that an ROV can work. So you have these trade-offs. Yeah, but I don't have a good, speed rating on the vehicle, unfortunately.
So as we're getting close to our hour mark, I wanted to wrap up with a concluding question for each one of you. In what advice you would give our viewers today if they would like to pursue a career in science? Maybe talk a little bit about how you got to where you are and what is your best piece of advice for our viewers today. Steph, why don't we start with you?
Yeah, I always loved science as a kid. And I had parents that really encouraged that, which I was really lucky to have. I guess my career path has been, I thought I was going in one direction. I really wanted to become a microbiologist and an immunologist and go down that sort of biology route. And then I found geology and found that I absolutely loved it, even though I didn't do it at school. And then I went into a different area of geology in sort of Antarctic geology and looking at glacial sort of environments. And now I've sort of, over this past week and over the next couple of weeks have taken another turn to look at marine science and work in the tropics. I guess my piece of advice would be, can I have two pieces? I'm going to have two pieces. I've got the microphone. Don't be afraid to change your tack. If an opportunity comes up, take it and be ready to take it and follow that. Where it goes. And it's to know where you want to go. And even if you don't, sometimes it's really useful to know what you don't want to do. So yeah, those would be my pieces of advice.
Those are great pieces. Alex, how about you?
So I always loved being outdoors. I knew I wanted to do something that involved being outdoors. I didn't really know exactly what that would look like. I sort of toyed with a few different ideas, but then I sort of went to uni and through that got exposed to geology and realized that just brought everything together for me. It was about understanding that natural environment, how things became the way that they are. And so for me, having that, something tangible to piece together, really made sense for me. And so I think my advice would be is to follow your interests. Think about what you love, what you enjoy doing, and work out a pathway where you can continue doing that. And I've been lucky enough that, I have a job that I just think is amazing and I really, really enjoy because there's just new things all the time and it takes me to amazing places that I never would have dreamt of seeing.
So for me, I'm coming at it more from an engineering standpoint. And I grew up and I always loved working with my hands. I also loved being outdoors, but I didn't really see a way those two could fit together. Oftentimes we have this sort of view of an engineer in a lab or, in like a shop somewhere. But there is a lot of space for engineering to go, out into the wild. One of the things I absolutely love about robotics is I'm sort of unfocused. And so I can work, my main work is in software, but I can also, get a little bit of experience in the electronics and the hardware and the field work. And the other thing I really love about it is though, even though I'm an engineer, I'm not a biologist or a geologist, but some of this work allows me to work with people that are in those fields. And you can see how the robotics can impact their work and allow them to do their work even more and give them extra tools that they never had before. So that's something I think is really, the thing I really love about it is that you get exposed not only to your own disciplines of engineering, but all these other things, all these other scientific disciplines. So even if you're not actively working in them, you can affect them in some way and make a difference in the amount of science we're able to do. So I think that's my favorite part about it.
That's always my favorite question to ask. It's always interesting to hear how people get to where they've gone. I really want to thank all of you for being able to spend some time with us today and share your advice and your experiences. And thank all of our schools and viewers today who have been able to join us. And I want to encourage everyone to please continue to follow Falcor's journey in the Great Barrier Reef at Schmidt Ocean. We are on Facebook, Instagram, and Twitter, as well as YouTube. All our dives are streamed live, so you can go and watch the dives happening in real time. And we've been diving every day. Peter, thank you so much for inviting Falcor to participate in National Science Week. I'd love to turn it over to you for closing remarks.
Yeah, thanks so much, Carly, and thanks so much to all of the scientists and ROV operators that we've been talking to over the last hour. Really incredible sound and vision. I hope all the viewers have been inspired by that today. I know just watching some of these things live from, where are we, 1,500 meters under the sea at the moment, really mesmerizing stuff. So what a wonderful opportunity. Thanks so much to Schmidt Ocean Institute and everyone on board the RV Falcor for participating today. I also want to thank the Sydney Science Trail for hosting us, and DART at the New South Wales Department of Education as well for helping us all. I hope that sends everyone off to their weekends on a really positive note. Happy Science Week, everyone, and we look forward to hopefully seeing you here at the Australian National Maritime Museum soon. Thanks very much.